So, my presentation is titled Regulation of Cell Number in the Planarian Schmidtea mediterranea. So, in addition to the planarians' remarkable ability to regenerate, they also can do this really cool thing where they can grow and degrow based on their nutritional status. And when they grow and degrow, they maintain their anatomical proportions. So you can see in this slide that as you starve the animals, their total body size is decreasing, but they're maintaining their anatomical proportions. So by the time you get to a small worm, it's not like you still have these huge photoreceptors on this tiny little body. They're maintaining the proportion. And this process is also reversible, so you can refeed the small animals and it will grow and once again maintain its anatomical proportions. And with the starvation, you can actually starve them for up to about 3 months. It depends on their original size. And they can get to be as small as 30 times as small as their original size. And when you feed them to their maximum size, they will split their body in half through a process called fission, where the top half of their body will separate from the bottom half of its body, and it attaches to a substrate or a surface and pulls itself apart. And then the top part will regenerate a new tail, and the bottom half will regenerate a new head, just like you saw in the previous presentation. So my project is looking into the cellular mechanisms that can explain degrowth and growth. So 2 logical explanations when you're trying to explain degrowth. The first one would be a change in cell number. So as you starve the animal, the number of cells would decrease, and as you feed the animal, the number of cells would increase. And the second explanation would be that it would be a change in cell size. So as you starve the animal, the cell size is decreasing, and as you feed the animal, the cell size is increasing. But we know from classic studies, like one study where they macerated planarians of all different sizes and then counted the number of cells they had, told us that it is due to a change in cell number that allows them to grow and degrow. So one explanation of a change in cell number would be a change in the rate of cell death. And some of you might be familiar with cell death. It's really important, especially during development, when in the womb our digits and our fingers and toes are all webbed. But by the time we're born, programmed cell death occurs and gets rid of those webs so that we can have individual digits and toes. So Dr. Pelletier in his postdoctoral work used a stain called tunnel, which is similar to the H3P stain that Amber, Stu, and Jade talked to you about, which is the antibody stain, except for tunnel stains for dying cells or cells undergoing programmed cell death instead of stem cells. So you can see in this starvation time course, 7 days post-feeding, there's a couple orange dots, and those orange dots are indicating cells undergoing programmed cell death. By 35 days post-feeding, there's more orange dots than in day 7. So this is suggesting that there's an increased rate of cell death during starvation. And the graph here is showing tunnel-positive nuclei, so a number of cells that have the tunnel stain showing. And then on the x-axis, you can see the days post-feeding. So as you starve the animal, the number of tunnel-positive nuclei is increasing, so the number of dying cells is increasing as you starve the animal. Then Dr. Pelletier at day 28 fed the animals again, and then you see this drastic decrease in the number of dying cells. Once you begin to feed the animal again, it begins to grow in size. So another explanation for a change in cell number could be a decreased rate of stem cell division, which I'm going to talk to you more about. So in addition to the stem cells and planarians that are important for regeneration, we also have stem cells and dying cells in our body that are maintaining our tissues. So this picture is showing your skin. And you're probably familiar that you're constantly shedding skin cells, but you're also shedding cells in your intestinal lining and in your blood. And it's possible that this process is happening in all tissues in your body. So deep in your skin, you have stem cells, just like you saw in the planarians. And as your dying skin cells fall off, these stem cells are differentiating or specializing towards the surface of your skin to replenish those cells that are dying and falling off. And to emphasize this point, I put this quote here, which states, "So massive is the flux of cells through our bodies that in a typical year, each of us will produce and in parallel eradicate a mass of cells equal to almost our entire body weight." So this is pretty incredible. You know, you're thinking you're just shedding some skin cells, but this process is so intense and so significant that it's estimated by John Reed that you may be shedding off so many skin cells that it equals your whole body weight. It's pretty cool. So again, my project question is, does stem cell division decrease during degrowth? So to approach this question, I set up a starvation time course. So you could call this day 0, where I fed my animals and then I isolated them from feeding, and I fixed and stained for stem cells at 4 different time points during my starvation time course. And like you saw before, as you starve the animal, it's decreasing in size while maintaining its anatomical proportions. So this is a video of a planarian feeding, and this organ here, like Amber said in the question session, is a pharynx, and allows the animal to eat and expel waste all at the same time. And in this video, the animal, or the planarian's eating brine shrimp, and the pharynx can also be referred to as a manus, because it's combining what we know as a mouth and an anus into one organ. So in the lab, instead of feeding them brine shrimp, sorry, it's kind of bloody, we feed them homogenized calf liver. So up here you can see, that's almost a whole liver, and we got 4 or 5 calf livers from an organic farm in Massachusetts Dr. Pelletier got for us. And we took it upstairs into the lab, and we ripped all the connective tissue out, and we ripped it apart, and eventually ground it down into a paste. And here you can see Josh from the lab is plating this paste into small petri plates that we freeze and store to feed our planarians throughout the school year. So this little equation is showing planarians plus their calf liver makes them happy and growing and full. So again, here's the degrowth and growth curve. So once again, you starve the animals, they decrease in size, they're maintaining the anatomical proportion I talked about before, and it's reversible, and you can feed them, and they'll regrow. So the experimental methods are similar to what you saw in the last presentation. So I started by fixing animals at 4 different time points in my starvation time course. And the fixation is simply just to kill the animal and preserve it in the state that's in at the time of fixation. And then after you fix them, I stain for stem cells using H3P, which is the same stain they used in FurbyCam1. And H3P is an antibody stain that's specific for a phosphorylation event during the cell cycle. So the stain targets the stem cells during that point of stem cell division. And then to visualize these fluorescing stem cells, we have a fluorescent scope, which Stu is a really great model using here. And we're really fortunate to have this awesome piece of equipment here at Keene State. It makes it really easy to do what we're trying to do here. And on the top of the scope, you can see there's a camera. So you can take live images, and it has a direct feed right into the computer. So you can do live, and you can focus with the scope and see what you're trying to look at on the computer screen, while also using the microscope itself. And then you can take your images, and once you have your images on the computer, we use a program called ImageJ. This is just kind of a print screen of that, where I sat there and looked at all these pictures and clicked on every stem cell I saw fluorescing. And that's targeted by that. So every little blue dot is where I clicked and numbered every stem cell. So, for example, this animal had 187 fluorescing stem cells. So here's some pictures from our results. And you can see up here, this is 5 days post-feeding, then 12 days post-feeding, 27 days post-feeding, and then finally 30 days post-feeding. And it's pretty obvious that right away you can see that 5 days post-feeding, there's a lot of green dots, so you have a lot of stem cells here. By the time you get down to 30 days post-feeding, there's a pretty obvious decrease in the number of green dots. So this is suggesting that there's a decrease in the number of stem cells with starvation. So here's a graph of the quantification of the average cell numbers per data set for days post-feeding. So here in the x-axis, you have 5 days post-feeding all the way through 30 days post-feeding, and these are each of my 4 fixation points in my starvation time course. So the average stem cell number in the animals 5 days post-feeding, and I had 7 animals in that data set, was 312 stem cells. By the time you get to 30 days post-feeding, and I had 7 animals again in that data set, it had an average of 138 stem cells per animal. So again, this is suggesting an obvious trend that there's a decrease in the number of stem cells with starvation. But these data sets are kind of small, they all have 7, except for in 27 days post-feeding, that data set only has 6 animals. So I'd like to increase the number of animals per time point and also increase the number of time points to kind of emphasize the trend that you see here. So I can conclude from these results that the number of dividing stem cells is decreasing during extended starvation, which likely contributes to a reduction in the overall cell number during degrowth, like I talked about at the beginning of the presentation. So next, I'm going to continue H3P staining, like I talked to you about a second ago, and increase the number of animals, increase the number of time points of fixation during the starvation time course. But I'd also like to double label using tunnel staining like Dr. Pelletier used in his postdoctoral work to stain for dying cells. That way we can determine the relative rates of programmed cell death to stem cell division during degrowth. So these pictures are ones that I took, and this is the H3P stain for the stem cells. This is the tunnel stain for the dying cells. This is the same exact planarian at the same exact time of fixation. So it's the same animal with both of these stains in it. So that way you can determine how many cells are dying and how many stem cells are dividing at the same exact animal at the same exact time point during starvation. And we'd also like to optimize the quantitative analysis to an automated cell counting software so that I don't have to sit there going blind, clicking every stem cell I see through the computer screen. We'd also like to identify genetic pathways regulating cell death and stem cell division, and screen for candidate genes that show increased expression in response to starvation. And Dr. Pelletier, again, his postdoctoral work right before he left Utah, he did a preliminary screen to identify some candidate genes that show increased expression during starvation. So we'd also like to further investigate the candidate genes that he found. So why is all this important? These are just worms, so cool, they can change their cell number. But this is has direct implications to human biology and human health. So an example is in cancer cells, you have this loss of programmed cell death, like I talked about, that Dr. Pelletier worked on. This, in addition to stem cells constantly dividing, you also have cells dying to maintain healthy tissues. So you can see here, this is normal cell division. So you have a cell, and it divides into 2 daughter cells, and then the daughter cells again divide into 2 more daughter cells. And here's an example where in one of the daughter cells, one of the cells is damaged. And in a healthy tissue, a damaged cell will be targeted for programmed cell death and be eliminated. But in cancer, you have that damaged cell, and something goes wrong, and there's all different things that go wrong, and that cell isn't targeted for programmed cell death, which leads to rapid, uncontrolled cell growth, which can lead to metastasis and tumor growth. Then another example is in obesity, and initial weight gain is associated with an increase in cell number, but it's also associated with an increase in cell size. So in these 2 fat cells, you can see the fat reservoir in this cell is a little bit smaller than the fat reservoir in this cell. So once you initially gain weight and you put those cells there, they don't die once you begin to lose weight. This is why it's really difficult to lose weight and then sustain that weight loss. Because even if you lose weight from dieting, you stop dieting, these cells are sitting there waiting for you to increase your calorie intake so they can store more lipids and then gain weight again. And another example is in aging, and there's a lot of different theories on aging, but one of them is that you have a reduction in the number and the function of your stem cells, which leads to aging. So all these things have implications to human health, and if we can understand how planarians can regulate their cell number, then maybe we could determine pathways to treat obesity patients or to help with aging and to treat different cancer pathways. So I'd like to thank Dr. Pelletier for all his help, and I'd like to thank Dr. Whittemore this year and Dr. Launen for the NIH-funded INBRE grant. I'd like to thank Dean Leversey for helping us acquire some really useful resources, and the Keene State College Biology Department for all of their support and the facilities. And I'd like to thank people in the lab, Josh, who's not here, but he helps out a lot, and then Amber and Stu and Jade, who you heard from before.
I'm doing my role. So I'm just trying to understand, so during degrowth, there's a decrease in cell number. And you're focusing on the stem cells.
Mhm.
And what's going on in the other cell population, like the mature cells? Are they decreasing in number? And like, is the decrease in stem cell number that you're seeing directly proportional to the decrease of all total cell number, or is it responsible for all the loss?
Well, that's why, and I tried to do the tunnel staining, and that's why I wanted to do the tunnel staining too, because if we could look at the relative rates of cell death, like Dr. Pelletieri did with the tunnel stain, then I could see how many cells are dying, and if there's also a decrease in stem cell number, because then the just regular programmed cell death could account for other cells dying instead of just a decreased rate of stem cell division, which allows for it to shrink overall. Because it's maintaining that anatomical proportion, you have to get rid of a lot of that other tissue, or you're going to have like this tiny little worm with huge photoreceptors going to look ridiculous.
No, I think that's fascinating to think about the so there's no reduction in cell size at all, or just very little, or that's just amazing.
It might be a little, it's like a small change in cell size.
Possibly.
Right?
So.
Yeah.
Yeah, but mostly it's just cell
Primarily
number.
Yeah.
That's interesting.
Okay, I'm wondering, how long did it, because you had 7 worms total, right, that you
7
found
worms for, well, yeah.
for 7, I guess you counted mini worms, but
Yeah.
7 worms per ton trial.
Yeah,
right?
I had about 7 worms for 3 of the 4 time points, and 1 had 6 that actually had like good stain, and that I used for those days.
I'm curious, how long did it take you? I mean, 'cause I'm thinking, that is an extraordinary amount of time. I mean, like you guys all must have worked a tremendous amount of time to get the data that you
Yeah.
got. So I'm just curious, how long did it take you
To do all the
get
counting?
Yeah, like if you had to guesstimate.
Probably a total of, I don't know, 7-8 hours
It's a
maybe.
long time.
Well, especially in the beginning, because I'd never done it before, so you want to be really careful. Like the picture I showed you, you can't see any more green dots, and you want to cover it. So I was like zooming in, and then you have to get up and walk around because your eyes start to cross. You can see green dots out there.
So that automated.
Yeah, Matt
that
tried to help me find
automated
something
counting,
too.
It's gonna be, it's gonna propel your work. I mean,
Yeah,
that's really
yeah.
gonna make you.
Well, if I could have
do a
data
lot
sets
more.
of 10, 20 animals and 10 time points, and then I could have a software that just looks at the picture and says, okay, there's 300 stem cells in this animal.
Yeah,
then
it's important
it would be
that you guys
much
get that.
easier.
Yeah,
Much easier.
Yeah, the software I use in a postdoc is a small fortune, so we're gonna figure this out with ImageJ, which Anna's actually already started.
Okay.
So we'll be able to do it. It's just gonna take some groundwork.
Right,
Yeah.
right.
We didn't have
That's
time to figure
That's
out most of
phenomenal.
the
It's amazing how much work you guys did. And just to maintain the worms too, like it's really phenomenal.
Thanks.
Excuse me.
Go ahead. Go. Yep.
Yes, a follow-up question to that regarding technique.
Yeah.
Because as I was listening to you, I was thinking, how would I keep track of which dots I counted and which dots I didn't? And I would probably have to count, I would probably have several false starts and have to restart counting. How did you keep track of that? Or was there a method?
I may have skipped over this part, and here it's kind of hard to see now the lights are on, but each little blue dot is my click. So me clicking on the picture itself on the computer screen. And
You
right
changed the
here,
color.
yeah. So, and there's actually a little number 1 on each blue dot that you can't see because it's so tiny from where you're sitting, but this counts it for you. So every time you click, it counts. So this had 187. And it actually, you can see 8 types. So say you had a sample that had different cell types, you could use a label that would be a different color and label it number 2. So you don't have to, I'm not like sitting there doing tallies or going 1, 2, 3, up to like 600 stem cells. So it actually keeps track for you, so you don't have to, if someone walks in the room, you don't lose track and have to start.
Yeah, I asked because I studied biology in the Middle Ages, and at that time we didn't have any software packages, and so we did have to devise techniques to keep track by hand,
Yeah.
both counting as well as to eliminate data points that we had already accounted for. So.
Yeah. No,
Thank you.
I
Great.
feel lucky to live in an age of technology where Matt.
Did you see any change in the distribution of stem cells over the course of feeding, or did it stay relatively uniform?
Well, it's kind of hard to see. Well, it's like they said, you never see them in the pharynx, in the middle. There's a couple dots, but there's nothing really. I didn't notice any trends. it may be more obvious if I was looking at more pictures, like the whole data set. If I took all of my photos from 5 days post-feeding and then compared them to 30 days post-feeding. But no, I didn't notice any real obvious trends. It's just a matter of quantity.
But it's a great question.
Yeah.
We could potentially address that too by taking sectors and looking at, and this is a pretty broad way of looking at the entire stem cell population, but there are subpopulations within that general population, and there may be changes within the subpopulation. So it's a really interesting question.
And I wonder if you would see something with a double staining procedure, if you'd see areas that were targeted for programmed cell death before other
More so
sections.
than others,
Mhm.
yeah. Because you could do a count per square millimeter, right? Yeah. Christine?
And how well does the stain like penetrate into the worm?
Well, it really depends on the size. Like with Amber, Sue, and Jade, they had their worms that they chose were a little bit too big, so they didn't get the stain to penetrate as well. And I had some variability, like the pictures I showed here were like some of the better ones, but there was a couple of my pictures where I had to kind of zoom in more. But I had pretty good luck with the animal size, I think.
So for a smaller worm, did you like consider the possibility that the staining could penetrate like a higher percentage of like the worm's tissues than like the larger worm before it started to like degrow?
It's a really good point. Well, what do you think about that, Dr. B?
Well, you're the speaker.
I think it makes sense because, like, you get more optimal penetration of the stain in a smaller animal. But I don't know if it. Are you like suggesting it might vary your data a little bit if you had an animal that was a little bit bigger and the stain didn't penetrate, but there may be stem cells there that the stain wasn't getting to or something?
Right, but I think it would actually support your data more because you would see like higher even though you saw like what fewer cells in like 30 days.
Yeah.
So you could say maybe even though higher percentage of the cells could have been stained.
Yeah.
So
because
it's
the
going to
animal's
actually
smaller,
further
so
support.
yeah. No, I get what you're saying. So the animal's smaller, so technically it should penetrate more, and you should get a more optimal stain, and you're still staining less.
Mhm.
So it's like a double emphasis on.
Yeah, so that's very good. And the other thing is you can also, we could cut them, dice them, and different sizes, and that'll give you an idea of the staining efficiency. And within this size range that we're looking at is not significant difference in staining efficiency. But that's the key point. It's if anything, if there is a staining issue, it's even working more in Anna's favor.
Thank you.
Is there any prediction for whether you think the rate of reduction in stem cells is going to be greater or less than the rate of cell number reduction in the other cell population?
Like, so the relative rate of stem cell division to cell death? I'm not sure if...
Cell death in stem cell population versus cell death in the differentiated cell.
Oh, okay, I see what you're saying.
Like, is there a prediction of whether you'd expect it to be slower in the stem cell population, or faster, or the same, directly proportional? I don't know if there was any background.
No,
You do have that?
No, it's not clear. It's an interesting.
Yeah, so you're
interesting
just,
question.
this is exploratory, just to see.
And we could potentially go after that with in situ labels of differentiated markers and stem cells, and combining it with the tunnel to see where it happens in the different cell populations. It's an interesting idea.
And are you gonna do regrowth, so go the opposite direction to see if, like, I'm not sure if that would show you anything different, but might it?
Yeah.
Like to say to take these ones that have degrown, is that actually a term? Yeah.
Sure.
Degrown and then regrow them
Yeah.
and see if you get the same
The
changes.
same kind of
and-
proportions are kind of
yeah.
repeating themselves going the other
Yeah,
direction.
do the stem cell population increase in rate at these various same rates?
Yeah, that would be really interesting to look into as well.
That's neat. I want to talk to you about tadpoles.
Uh-oh. Yeah. Any other questions?
Thank you all for coming.